All right, so welcome to lecture 11. So today we'll be starting a new chapter. In the textbook, it's chapter number 6, where we'll be studying various properties of the maximum likelihood function. Yeah, so let's get started. So if you recall, in the chapter 4, we studied to some extent this maximum likelihood estimator. Let me remind you what it is. So this chapter is called, that you're going to start today, is called the maximum likelihood methods. Okay. Now, what we are going to start with, let me remind you what we had before. So suppose we have a random variable x has a PDF f of x theta, and this theta is unknown. Okay. So the PDF depends on some unknown parameter theta, and we usually take theta to be, it's unknown, but we know that it's in some set omega. So now, how do you estimate this theta? So that's the question of this entire maximum likelihood method section. What we did before is, suppose that we have a random sample. So this is just a refresher. If you have seen it before, that's fine. But this is just a refresher from chapter 4. So draw a sample. So sample is x1, x2, all the way up to xn. So these are IIDs, and the distribution is x, right? So these are IID with PDF f of x theta, where theta is in omega, as I wrote it before. Remember, there are two-step procedures. Step 1 is you construct this this likelihood function. So likelihood function in this case is given by theta x, which is the product of the likelihood functions for these different random variables. Okay, so basically what we did for each sample x1, x2, xn. So for each of these, our probability density function is f of xi theta. So little xi is the values. And so this xi can, so basically it's f of x1 theta times times f of x2 theta, so on. So this xi just signifies different random variables, right? Corresponding to, or different sort of the variable which this which this probability density function is taking. Okay, we have seen this example before. Now, what we did is we take the log of this function and we denote that little l of theta to be, so it's a log likelihood function, which we denote by little l of theta, which is log of l theta. Okay. So this is same as, if I just drop this x, okay. Which is given by summation I from 1 to n. If I take the product of this, if I have a product and take the log, it becomes a summation. It becomes log of f of xi theta. Okay, so that is the log likelihood that we discussed before. You can always insert the x here, but I'm just writing this in terms of this theta. Okay, because that is the unknown parameter. How did we do it? How did we find this theta? We maximize this thing. Okay. So a point estimator, an estimator of theta is given by theta hat, which is a function of all these random variables. I'm writing x estimator, so therefore, in terms of all these random variables, I'm writing it, where this theta hat maximizes maximizes the function L theta. Consequently, it maximizes this little L theta too, right? Because log is an increasing function. Okay. We have done all these discussions in the previous chapter. So how we find it and how we can compute it for a given case. Another important aspect can be, so suppose, this suppose there is a way that we are guessing this theta, and suppose we are saying that theta sub 0 is the true value of theta. Okay. Now we can do a hypothesis testing that, okay, is the true value of theta be if it's really theta 0 or not. Okay, so that can be a hypothesis testing. First of all, we'll be doing all these things in this section, but first of all, let's in this section we'll be assuming some conditions which are called the regularity conditions. So let's start with the assumption, so which is the so-called the regularity conditions, which is needed for studying this in details. There are three conditions: R0, R1, and R2. What is the first one, R0? So we'll be writing this in the following way. The CDFs are distinct. Okay, that is, if theta is not equal to theta prime, then f of xi theta is not equal to f of xi theta prime. Okay. That means if we have two distinct parameter values, then consequently, what it says is their CDFs are different. So this means that the parameters identify, because if I differentiate it, I'll get the PDF. So let's write identify the PDF. Okay. So that means we are saying that as soon as we can find theta, we know the distribution. Okay. So and also if we have two different values of theta, then they're not the same, meaning that they'll be slightly different or they'll be different. That's my first assumption. Second one, number 2, it's called R1. It's given by the PDFs have common support for all theta. What does it mean? So that means if, well, so what is the support? So support is the point for it's is a set when it's non-zero. So if at some point of time, say f of xi theta equals if 0, let's write this in terms of PDF. If f of xi theta is 0, then f of xi theta prime is also 0, and vice versa. Okay, if at some point it's 0, then the other one is also 0 if so, meaning that suppose we have something like this one, say I don't know, suppose if you have something like this one for f of x1 theta, and something like this one, I'm just randomly cooking a picture. maybe something like this one, as f of x1 theta prime, you see that they have their support is the same. So this is inside. Okay. And we are assuming that for every parameter, for every parameter values theta, so this is their support is the same. Okay, so support does not depend on this on this parameter value. It's sort of restrictive, and later on we'll be doing some examples where we'll not really follow this one, but let's temporarily keep it, because for the next result we'll need it. Not for R2, but I'll write this later. Okay, and finally we assume the point theta 0. What is this theta 0? Theta 0 is the true value of theta. True value of theta. That means whatever maximizes the log likelihood function. Okay. So we assume that the point theta 0 is an interior point in omega. Okay, meaning that what is omega? Omega is a set of all such theta values, and we are assuming that this whatever the maximizing value is, that is an interior point of this set. So that means it's not in the boundary of omega. Okay. Let me remind you what omega is. Omega is the all possible values of theta, right? So omega is the all possible value of theta. So so what we are saying is that the true value is always an interior point of all possible values. So that means the true value is not appearing on the boundary. Okay. It's mostly for a technical reason. We'll see later. Okay. Now, based on this one, are we ready to write the theorem, which is sort of the main theorem? What we are going to show is the following. So here is in words. So we will try to show that the L theta asymptotically separates theta 0, which is a true value, from, so I wrote theta 0, true value of theta right here, from other thetas. Okay. From models from other values of theta which are not equal to theta 0. So this is the, I'll write this formally, but what I mean by asymptotically separating this true value from the other values, it'll be more clear when I write the statement, but this is the summary of this one. Okay, now let me write this. Assume that, so here is the actual content of this theorem. Assume that theta 0 is the true parameter and that expected value of f of xi theta over f of xi theta 0 exists. Now, for those, for it must be for all of you. For you know what the expectation is, right? So how do you compute this expectation? So you need to, when you compute some expectation, you have to say like with respect to which probability measure you're talking about. Now, in this case, apparently, I have two different probability measures in the sense that do I take this one or do I take this one as a PDF of xi? Okay, because xi has two PDFs, right? So one PDF is theta, one PDF is theta, one PDF when the theta is just theta, any value, or other one is when theta is replaced by theta 0. So I'm writing this with respect to, I'm taking the expectation with respect to theta 0. Okay, meaning that when I'm talking about PDF, I'm talking about the PDF with respect to theta 0, right? PDF depends on the value of theta, and the value of theta is theta 0 here. Okay. Now, under assumptions R0 and R1. Then I'm trying to write this statement mathematically. It goes like this: limit n goes to infinity, p of theta 0, L of theta 0, comma, x 1. So basically the same x as I have here. So here this let me just write. So here this x is the random variable, right? So I'm talking about the same x. If it makes it a little better, maybe I can write it here. So this x is actually a vector because this x depends on all this xi's, right? So it's where this x is really say x1, x2, xn. Okay. So this x, and also I can write this in a vector notation, so but I'll not do it here. So this x is really a vector, which is given by this one. Now, what we have here is the following. So here this x, which is a vector, this really x is really x1, x2, xn. Okay. So what we want is this one is so suppose I subtract or let's compute this probability. This bigger than L of theta x. This is equal to 1 for all theta not equal to theta 0, where theta 0 is a true value. So this is a beautiful theorem which shows that, let's see what it shows. So it says that it shows that when n, so when your sample size is going to infinity, that is another way of explaining this is it's saying asymptotically. So something is happening asymptotically. So what is happening? So that probability that L of theta 0 x is more than L of theta x. So this likelihood function is more than this likelihood function under the assumption that the actual parameter is theta sub 0. So that probability is going to 1. Okay, as long as this theta is not equal to theta 0. So that means it's clearly separating. So that's why this is written here. So L theta asymptotically separates theta 0 from other values of theta. Okay, so this is the meaning of what we've written here. Okay, so that means eventually this log likelihood function wins over all other. Let's prove it because it's not really hard to prove, and it'll give you a nice exercise on how to prove this kind of things. So let's see what we have to do. So proof. If L of theta 0 x is bigger than L of theta x, that means that I'm writing the last the statement which is inside. Let's see what it means. Suppose I take the logarithm of both sides. Okay. So then logarithm of theta 0 x minus logarithm of L of theta x is bigger than 0, right? Now let's see if I can compute the logarithm of this one. So I have written this L of theta log of L theta right here. So that is the formula. So it's summation of log of f of xi theta, right? So I can do this following here. So this is going to be summation I from 1 to n f of xi theta 0, sorry, log of this minus summation I from 1 to n log of f of xi theta. So the only difference between these two is here is theta 0 and here is theta. So this is coming from here, this is coming from here. That's it. That's the only difference. If I just rewrite it, so that means I get summation I from 1 to n. So there are a bunch of logarithms and logarithms follow. So if I subtract this one, so I can pair this and this. So I can write logarithm of f of xi theta 0 over f of xi theta bigger than 0, right? And therefore, suppose I want to see the negative side of it. So if I write, say, if I flip the factors, so there is a numerator and there is a denominator. So suppose I swap this numerator and denominator, then I have I from 1 to n. That will give me a negative sign. So f of xi theta, f of xi theta 0, this is less than 0, right? By flipping the two fractions. Now this is true for every such thing. So if I multiply this with a positive number, namely 1 over n, nothing changes. So let's multiply that with 1 over n, and we have xi theta, f of xi theta 0, less than 0. Good. Okay, let's keep this in mind. We didn't prove it, but it's very useful. Now at this point, let me just mention to you something which is something you must have seen in the previous version of the course or somewhere. Okay, it's an aside from a previous class or something. It's called the Chebyshev's inequality. So sorry, Chebyshev's inequality we did. I meant Jensen's inequality. Jensen's inequality. What is that? Let me just write the statement here. So it says that if phi is convex on an open interval I, and x is an random variable, an RV, whose support is contained in I, and has finite expectation, then phi of E of x is less than equal to E of phi of x. So basically, if you interchange phi and E for a convex function, so when you have E outside, its values move. Also, if this phi is a strictly convex function, then this inequality is a strict inequality. So this is something which you might have seen, or you must have seen in one of the previous courses. Okay. This result has independent interest in many other disciplines. Now we'll be simply using this result. So for our purpose. So what do you want to do? So let's see. Let's see an example of a convex. So it needs. I mean, if I want to use an Jensen's inequality, the function must be a convex function. Okay. By the way, let me just write it for strict convex function. Less than equal to becomes strictly less than in the above, right? So there is a less than equal to sign, so that becomes strictly less than. Okay, now an example of a strict convex function is negative logarithm. Okay. Let consider, say, phi x equals to minus log of x, which is strictly convex. convex function. Okay. Now I'm thinking about this quantity. So just keep that in mind. I'll be using it. Let's now do some computation with this one, and then I'll be using this log thing. Okay, so what I'm trying to do is the following. So let's see. Let's start with the left-hand side of this one. So let's start with this quantity. Okay. So 1 over n summation I from 1 to n f of log of f of xi theta over f of xi theta 0. I wrote what we had there. I am saying that this in probability, now this by the law of large number, where does it go? So by the law of large numbers, it says that if you have a bunch of terms like this one, they are IID, by the way, because xi's are IID and these quantities are functions of xi, so they are IIDs. So by law of large number, this goes to this whole summation of this random variables over 1 over n. It goes to the expected or the mean of this individual ones, right? And since they're IID, I can say that they're going to the mean of same theta of 1, right? So I can write this as they're going to e of log of f of say a particular one, x1. There's nothing special about x1. You can replace this by x2, x3, whatever. x1 theta over f of x1 theta 0. Okay. And by the way, since we have various expectation, I mean, we have various kind of various random variables with different parameter values. So I'll specify here. So I'm taking the expectation with respect to theta 0. So that means when I take the expectation, my PDF is given by this one. Okay. So this is something we get by the law of large numbers. This one. Okay. Now, one more thing you have to be really careful about. So whenever you are considering this, so whenever we are having this quantity, I don't want this f of x zero, which is the first assumption for regularity. We know that if thetas are different, then these two are not the same. So by this, the right-hand side is not equal to 0. Here we use the assumption R0. Okay. Now this log function, as we have seen, it's a strictly convex function, right? And therefore, we can so minus log function is a strictly convex function, because if I just draw the log function, it looks like this. So log of 0 is 1, something like this one. So this is log function, log of x. If I take the minus log of x, it will be just opposite of this one. So this is minus log of x, right? So minus log of x is a strictly convex function. So this relation in terms of logs. So if I, by the way, if I change this, I mean, what I'm trying to say is the following. So minus log of, if I use the Janssen inequality, minus log of e of x would be less than equal to e of minus log of x, right? By the Jensen's inequality. Gives me this. And hence, if I multiply by the negative sign, and this negative sign comes out, so log of e of x, by the way, it's a, so log function is a strictly convex function, so it's strictly less than. Okay? So minus log x is strictly convex. And hence, this inequality is strict. So then log of e of x is bigger than equal to e of log x, right? Because if I multiply with the negative sign, the inequality changes. This is just an aside. You must be familiar with this one anyway, but I'm just mentioning it here. So therefore, I can do the following. This quantity right here, so this is basically e of log of something, right? So it's less than, strictly less than log of e of that thing. And the strict inequality is important. Log of f of x1 theta over f of x1 theta 0. Okay. And this is by Jensen's inequality, what we have just done. Okay, now let's compute this. We are done. So basically, let's now compute this right side. However, but what is this quantity? E of theta 0, f of x1 theta over f of x1 theta 0. How do we compute this? So this is basically integral of f of x theta, f of x theta 0. And then since it's an expectation with respect to theta 0, so I have to multiply with f of x theta 0 dx, right? From minus infinity to infinity. Okay. Now, please note that one more important thing here is R. So the assumption R1 is in play. So we don't want to divide by 0 here. So using, so here we have seen where R0 is used. Now use R1 to conclude or to implement that the support is common. Okay. Otherwise, what happens is, suppose there are points for which it's non-zero, the denominator is 0, so then you're basically dividing by 0, so we are in trouble, right? So therefore, we are basically implementing R1 here. Now here, you can just cancel this one. So what you have is minus infinity, infinity f of x theta dx, but this is a PDF, so this is 1. Okay. So hence, what we have here is the following. So therefore, what we have here is this quantity is really, we found it to be 1. So therefore, 1 over n summation I from 1 to n log of f of xi theta over f of xi theta 0 it's going to something. So it's going in probability to something which is less than 0. Do you agree? It's going to, in probability, to this object which is strictly less than 0. So that means it's going to a negative object in probability. Okay, and that's pretty much it. So that's what we wanted to that's what we started off with. So we assume that, remember that if this is because if this is true, so this is our first feature. So if whatever we are trying to prove is true, then this is less than 0. So we showed that indeed this quantity is less than 0. Okay, in probability. In probability means so this is less than 0 in probability. Uh, um, so hence we conclude from here that L of theta 0 x is bigger than L of theta x as um, in probability and when n is going to infinity. That's the meaning, right? Another way of writing this is the following. So limit n goes to infinity, probability of theta 0, L of theta 0, x, where x is a vector valued function, x is a vector, so it's L of theta x is 1. Hence, so let me just write by the star, and star is right here. I don't know, by the 1. 1 is right here. So we see that, so once again, just to go back, we see that this statement is equivalent to this statement, right? And then we started off with this one, and we showed that in probability, so as n goes to infinity, in probability, this is true. So that means as n goes to infinity, in probability, this is true. And another way of writing the same thing is this one. That's it. So this is how we prove this quantity. Okay, now we have a lot of applications of this beautiful result. So let's first write one application. So here is a definition of the maximum likelihood estimator. Okay, so we say, by the way, I'm consistently using x equals to x1. It's a vector, x2, xn. Okay, so we say that theta hat, which is theta hat of x, is a maximum likelihood estimator, or in short, MLE, of theta if theta hat is the argmax of L theta x. So we have done this before. It's nothing new. It's just a statement. Okay. Okay. That's just a definition after all this. Example. So let's see if we can find one example. The first example that we'll be doing is the following. Here. So this is about the Laplace distribution. Okay. Let x1, x2, xn be IID with the density f of x theta equals 1/2 e to the minus x minus theta, an absolute value. Okay, so where this minus infinity less than x less than infinity and minus infinity less than theta infinity. So that means the omega, the big omega set is minus infinity infinity. So omega is minus infinity to infinity, okay, where theta belongs. Okay, this PDF is referred to either the Laplace or the double exponential distributions. This is the Laplace distribution or the double exponential distribution. What is the goal? I'm trying to estimate theta. As simple as that. Now let's do that. Let's take the likelihood function. Let's check the likelihood function. So L of theta, I'm dropping the x's. So what is L of theta? It's a product of f of xi theta, I from 1 to n, right? So in this case, it's going to be, let's see, I from 1 to n, 1/2, and then we have e to the minus xi minus theta, right? So let's compute the little L of theta, which is the log of L theta, which is the summation of all this because it was a product now. So it's a product, a summation of I from 1 to n uh, log of 1/2 plus log of e to the minus xi minus theta, right? So this is basically minus 2 minus log 2, and you have n of those. So it's basically minus n log 2. And here it's e to the power something. So it's minus, with the summation, it becomes I from 1 to n xi minus theta. Okay? So that is my log likelihood function. So the only parameter is theta. So the dl d theta, what would that be? This function is independent of the theta, so it's 0. Now this function is the absolute value function, right? So absolute value function. So I mean, if I try to differentiate this in the classical calculus, it's non-differentiable at 0. But other than the point 0, it's differentiable. If x is bigger than 0, it's plus 1. If x is less than 0, it's minus 1, right? The function is not differentiable at 0. I can write this as the sine of x. And in fact, they are distributionally equal, meaning that so there's a theory of distribution which shows that this derivative is actually equal to sine of x in distribution. Okay, we'll not go into that. Don't worry about it. But what we are trying to say is basically, if I differentiate the absolute value of x, assuming that x is not 0, what it gives is basically whatever the original sign of x is. If x is positive, it's returning plus 1. Sine of x means it's positive. It's plus 1 when it's basically right here. Sin x by definition is this one. Okay, so therefore what we get is this is 0. Now this one is going to be minus. So if I differentiate this one, it's summation I from 1 to n. So it's sine of xi minus theta. And then I have to differentiate, it's a chain rule, so I have to differentiate theta, so it's a minus 1, right? So what I get is I from 1 to n, this negative sine of xi minus theta. Another way of writing this is sometimes written as SGN. Okay, same thing. So now, so dl of d theta is basically equals to this one. Um, what we want to do is we want to have a value of theta for which it's true. Now look at this. So we have x1. So it's so sample values are x1, x2, x3, n minus 1, xn. So these are the values of x, right? Now, depending on I just ordered it in a nice way so that I mean I can see it, but the order is really not this nice, meaning that I may start, I mean, have x1 here, I may have x2 here, I may have x3 here, I can have xn here, I can have xn minus 1 here, maybe I have x4 here, who knows? Okay, so when I see a sample, it's something like this one. What I want is the sum of this sample to be 0. Okay, now the way to do it is, I mean, there are ways to do it. Um, the way to do it is choosing whatever that the theta value is in the median. So suppose theta is the median. What does median mean? It means that if there are even number of values, so suppose we have 4 numbers, so maybe 1, 3, 8, and 100 maybe. Okay, so what we consider the median to be is basically you have 4 numbers, so its median should be somewhere here, and then you take the average of like it's a midpoint between 3 and 8. So whatever that is a median. However, if we have say 5 numbers, so suppose we have another 6 here, then the median is 6. Okay, it's a value that appears at the very middle of the data set. You see that if it's some if there are odd number of if n is odd, and if this theta is chosen to the median, then exactly so it has same number of positive values and same number of negative values, so it cancels, and the median value is picked up as the one that is giving it 0. And if there are even number of values, so then theta is somewhere in between, so it's basically picking up same number of pluses and minuses. So the conclusion is, so this theta can be taken to be as a median of x1, x2, xn. So basically, we are estimating theta with this one here. I should also mention one more thing. So this is a solution for this for this estimating equations, meaning that this equation that we wrote here. So we found that so from here, so that means if dl d theta equals to 0, then we have this one, right? So this equation is the equation for finding the possible candidates which are the maximum likelihood estimator. So here, if you put theta equals to median, then we are seeing that the first partial is 0. Now for the second partials here, everything will be 0, right? So we cannot really have the second derivative test. So I mean here we will just leave it as at the point that we are saying that I mean second partial will not compute it. Okay, so let's all right, quick comment regarding this discussion. What we have just done is mathematically not very sound, so I thought of just mentioning a couple of things. One is, once again, for those who forgot what the definition of a medium is, so suppose we have a sample, say, y1, y2, yn is an ordered sample. Okay, so in this case, we define the sample medium. So this is the ordered sample. Okay, so that means so suppose for the original samples, what is given in the original sample, so we just order it. Now, the sample median. So in this case, the sample median is given by Q2, which is depending on n or even or odd. If n is odd, odd is easy. If n odd, then it's a mid one, which is y of n plus 1 over 2. And if n is even, then it's going to be y of n over 2 plus y of n plus 2 plus 1 over 2. Okay, so what does it mean? Simply, if I have, suppose, say 5 samples, say we have x1, x2, x3, x4, x5 ordered. Okay, so then in this case, x3 will be this will be the median. However, if I have, say, y1, y2, y3, y4, then the median will be y2 plus y3 over 2. So you just average this, okay, depending on the even and odd. Okay, now, so my comment here for the last problem is whenever we are doing this, so basically we didn't even do a secondary test, and we sort of differentiated non-differentiable functions. So I think a more accurate way of doing this will be the following. So this is coming from the fact. So back to the last problem. The last problem. So what we really have is we are trying, so we have this log likelihood function, which is something like this one, right? N log 2 minus I from 1 to n xi minus theta. And we are trying to maximize this. So basically, so maximization of L theta depends on, so because this is a constant term, now this is maximized provided this is minimized, right? On, or the same as, the minimization of this quantity, I from 1 to n, xi minus theta. Okay, now this is a very well-known problem. So how to like minimize this quantity for various cases. So what we can do is, for example, just for in order to us to think. So suppose we have just 2 points, say x1 and x2. Right? So you can think that you can define a function, say f theta, which is x1 minus theta plus x2 minus theta. Now you can easily check that for this function, so this function takes the form f theta. I'll not show it. I'll leave it up to you. So f theta, its value is say b. So if the theta is here, its value is b minus a. If x1 less than theta less than x2, its value is if its value, if theta is bigger than x2, its value is 2 theta minus x1 minus x2. And if it's if theta is less than x1, its value is x1 plus x2 minus 2 theta. Meaning that if I try to plot it here, it will look something like this. So if we have x1, x2, and if I plot it, it will be something like this. So first it will have the slope negative, and then here it's flat, it's b minus a, and then it's positive. So this is b minus a, and this is 2 theta minus x1 minus x2, and here x1 plus x2 minus 2 theta. You see the slope is negative here, slope is positive here, and in between it's flat. Okay. So you see that the minimizer, so argmin of f theta in this case would be any theta between, so any theta between x1 and x2, right? In particular, we know that in this case, the median lies here. So median here is median, and mean is x1 plus x2 over 2. So that means, in particular, I can take it Q2. Remember, Q2 is the median. Okay. Now, if you have, say, 3 points, say if we have x1, x2, and x3. Okay, so in this case, I can show that again the same thing. So f theta would be x1 minus theta plus x2 minus theta plus x3 minus theta. And I'm trying to minimize this quantity with respect to theta. It can be shown that f theta in this case, when you are between x1 and x2, so basically when you are between x1 and x2, so its value is minus x1 plus x2 plus x3 minus theta when x1 less than theta less than x2. So when you're here, your value is minus x1 minus x2 plus x3 plus theta when x2 less than theta less than x3. Finally, if your value is more than x3, this will be 3 theta minus a plus b plus c. Okay. And the other thing, of course, when this theta is less than x1, its value will be, sorry, there's no b, abc. It's x1 plus x2 plus x3. And it will be x1 plus x2 plus x3 minus 3 theta. You can just check by just expanding this expression based on the various things. In particular, this picture will look like this. So first of all, it will go down like this, and then it will go further down, and then it will go up, and then it will go further up. So it's symmetric. My drawing is not good, but so here it will be minus x1, depending on if this x1, x2, x3 is asymmetric. If not, I mean, it will be of course asymmetric. So it's minus x1 minus x2 plus x3 plus theta is this part, and then it becomes 3 theta minus x1 plus x2 plus x3. And then here it is minus x1 plus x2 plus x3 minus theta. And here, basically, x1 plus x2 plus x3 minus 3 theta. And you see the minimum appears here. And this is the median because there are 3 points. So this is the median. Okay. So in this case also, so we can say argmin theta, f theta, would be actually x2, which is q2. Okay. So hence, this quantity, basically this quantity, summation xi minus theta, I from 1 to n, is minimized at theta equals to q2. And that is something we used in the previous one. Okay, so this is just an aside, I mean, because the last one was not very mathematical. Okay, so let's continue with another example, say this one, which is for the logistic distribution. So here is an example, which is called the logistic distribution. Okay. Now these are very much similar to what we have done earlier. Like we found the maximum likelihood estimators for various cases. So these are some sub examples of what we have already done. This will be useful for the next classes. Let x1, x2, xn be IID with density f of x theta is e to the power of minus x minus theta over 1 plus e to the power of minus x minus theta squared. Okay. For minus infinity less than x less than infinity, minus infinity less than theta less than infinity. Okay. Let's compute find the maximum likelihood estimator of theta. So let's compute this. So basically, we found first of all solution. We can just start with the quantity log likelihood, the likelihood function, which is the product of I from 1 to n f of xi theta, which is given by product of I from 1 to n e of minus xi minus theta over 1 plus e to the power of xi minus theta squared. Okay, I'll not simplify it. I'll just take the log one. Right? L theta, little l theta is the log of L theta, which will be in terms of the summation, right? So summation means I have to take the summation of this one. So basically I have minus summation of I from 1 to n xi minus theta, right? And then minus, I have to compute this one. So it's 2 summation I from 1 to n log of 1 plus e to the minus xi minus theta. So this is going to be, note that this xi is a sample value. So x1, x2, xn are the values, sample values, observed values. And x bar, little x bar, which is 1 over n summation I from 1 to n xi, is the observed mean from the sample. It's not the sample mean, right? It's an observed sample mean. Sample mean is a random variable. Observed sample mean is something you can see. Now note that I can see it here. So xi summation, so that is basically n times x bar. So it's minus n x bar. And then minus, there's theta, but there are n of those, so it's n theta. And then minus 2 summation I from 1 to n log of 1 plus, I'm just writing this thing, 1 plus e to the minus xi minus theta. Okay, that's my L theta. Hence, if I differentiate this with respect to theta, I'll get what? So if I differentiate, the first term is independent of theta. Then the second term, sorry, there should be some, so there is a negative sign here. So it's minus it, it's plus n theta, right? Okay, so now if I differentiate this is going to be n. And now this whole thing, it depends on theta. So let's see. So minus 2 summation I from 1 to n. It's 1 over 1 plus e to the minus xi minus theta. And then I differentiate this one. So it's e to the minus xi minus theta. And then when I differentiate with respect to theta, it's 1, right? So this is this quantity. Okay. So dl d theta equals to 0 implies n minus 2 I from 1 to n e to the minus xi minus theta over 1 plus e to the minus xi minus theta equals 0. Okay, which is really equal, meaning it's I from 1 to n e to the minus xi minus theta 1 plus e to the minus xi minus theta equals n over 2. So this is the equation that governs how we should choose xi's so that I can make dl d theta 0. Now let's see if we can show that whatever we get here is an unique solution. So I can do it in the following way. So here, what we're trying to show is, I'll simply write that it can be shown that this solution that we obtain, let's call it 2, the solution that is obtained into is unique. Okay. All right. Also, let's compute the second derivative for this one. So with this one, also, it involves some computation. The second derivative, d2l d theta 2, is strictly negative. It can be shown. Okay, it's almost, we have done it right here. So this is dl d theta, and it's not really hard to do it. For example, if I differentiate it once, this will go away, and only this one. It's very easy actually. Okay, try it. If you have any questions, send me email. Easy. Okay. That means the solution 2 is giving you the maximum. Okay, so the solution of 2 gives the max of L theta. So that means that is the maximum likelihood estimator. Okay, so hence we found MLE for theta based on this method. So the MLE for theta can be obtained from this one. So basically what we have to solve this equation, I from 1 to n e to the minus xi minus theta 1 plus e to the minus xi minus theta equals to n over 2. Remember that when we observe the values of xi's, we know this number. So the only unknown in this entire equation is theta. So you can solve for it and you can get the solution. And that solution would be the maximizer of the log likelihood function or the likelihood function. And hence, that is the solution. Okay, so that's the maximum likelihood estimator. Okay, let's do one more problem, and then I'll mention something which is curious. But before doing that, let me just say something about this one. So this is problem number. I don't know if I did it earlier, so let me just do it anyway. So this is another problem. Uh, find example. Find the max MLE, maximum likelihood estimator, for P in X follows binomial NP. Okay. So it's a discrete version. So here, the log likelihood function solution. So the log likelihood function here, the theta is P, right? L of P is product of P of X equals to xi, and so so we have a total n trials. So I from 1 to n, right? So what is that? So this is going to be product of I from 1 to n, and this quantity is let's consider a sample. So I just want to make it a little more involved. So let's consider sample size of n. So sample size is n. So that means I take x1, x2, xn, where each of these xi's follow binomial, say m comma p. I'm just writing like two different letters. So their sample size is n m, and this is, let's make it m. Of course, this is true when m and n are equal, but let's consider the general case. So this is going to be m choose xi, p to the xi, 1 minus p to the m minus xi. Okay, so therefore, when I compute the log likelihood function, so let's compute the log likelihood function. So log, so it's L of P, which is log of LP, which is given by taking the logarithm of everything. So it's a log of, let's see, the first term, product of I from 1 to n, m choose xi. And then I can write plus the second term, which is log of P summation xi. And then the last term, so I'm just writing from here. Okay. The last term is, we have 1 minus P, log of 1 minus P, summation of this last term. Okay, so plus log of 1 minus P and summation I from 1 to n, m minus xi. Okay. Out of this one, let's write one more simplifying step, and then I'll have some comment. So the first term is log of I from 1 to n, m of m choose xi. Second term is log of P summation I from 1 to n xi. Third term is plus log of 1 minus P. When I take the summation m times n minus summation I from 1 to n xi. Okay. So this is my L of P. This is a constant. This constant does not even depend on P. It's independent on P. Okay. So now, if I mean, one more thing I can do, I can just simplify a little bit. So I can observe. So this once again, x1, x2, xn. So these are observed sample. And we define x bar to be the observed mean, which is given by 1 over n summation I from 1 to n xi, right? And here, whatever we're having, so all these are sort of observed sample, right? So I can write this quantity as, let's, I don't want to carry this term. So let's call this one, say m. Call it m. Okay. Plus, this term is n times x bar, right? So it's log of P times n times x bar. Finally, this term is plus log of 1 minus P. And then we have nm minus, so this is n times x bar again. Okay. One just last step to simplify this thing. So it's basically, it's a, I can write this as m plus nx bar log of P. I can pull out n from here, so it's plus n m minus x bar log of 1 minus P. Yeah, so that is a simplified version of LP. Okay. Differentiate it. So DLP dP, which will give me nx bar over P plus n m minus x bar 1 minus P, and then a negative sign due to this minus P. So if this is equal to 0, and if I solve this one, you can show that this will give me x bar minus x bar P equals to MP minus x bar P. And this is giving me P equals x bar over M. Okay. So dP equals to 0 gives me P equals to x bar over N. So this is a sample mean, like observed sample mean. If I'm dividing by M, what is M? So M is the population from where the samples are drawn, the size of the so remember, so each of those x's follow binomial MP. So this is that M. right? Also, will that make will that make my LP the second derivative minimum? So let's compute the second derivative. So what is the second derivative? I already computed the first one. So the second derivative of L with respect to P would be what? So it's basically minus n x bar over P squared. And this is minus n m minus x bar. And then it's minus, so it's becoming plus 1 minus P squared. See, I mean, it's very easy to show this. I mean, I think I made a little error somewhere in the calculation. So I think this one, when I take the second derivative, it becomes, the first one is this one is fine. The second one got to be negative, right? So the second one got to be negative. So what we have is the second derivative n x bar over P squared plus, sorry, minus n m minus x bar over 1 minus P squared. So at the point P equals to x bar over m, this becomes minus n x bar over x bar over m squared minus n m minus x bar 1 minus x bar over m squared, which is, so minus n x bars cancel, so it's n m squared over x bar minus n m minus x bar. There's m squared coming up, and then here it's m minus x bar squared. And here it becomes with a negative sign and n out, m squared out. So it's x bar m minus x bar. It's m minus x bar plus x bar, which is minus n m squared times m over x bar m minus x bar, and everything here is positive, and therefore with a negative sign it's negative. Hence P equals to x bar over m maximizes LP. So MLE for the binomial case, so MLE for this sample that we are discussing, for the sample x1, x2, xn, that is from with xi's from binomial MP P from the sample is given by P hat equals x bar over m. And that's a very well-known result for the binomial sample. Okay, so we compute the sample average and we divide by the population size, okay, by m, so the number of trials. Okay, so this is a result. Now let's mention one of the very important results for the maximum likelihood estimator, which is called the invariance principle for MLE. So I'll write this here. So it's called the invariance principle of MLE. Okay, it goes like this. Let x1, x2, all the way up to xn be IID with the PDF f of x theta with theta in omega for a specified function g, let us define eta equals g of theta be a parameter of interest. What are we trying to do? So basically, so theta is basically the unknown that we try to estimate using the maximum likelihood estimator, and suppose we found it. Now, suppose we are considering some eta equals to g of theta for a particular function g. Okay. Now, suppose that theta hat is the maximum likelihood estimator of theta. Then g of theta hat is the maximum likelihood estimator of eta, which is g of theta. So this is a pretty simple property, but it's of highly it's one of the most significant properties of the maximum likelihood estimator, as we'll see later, because it's very useful. We can use a lot of different um, like we can use this for a lot of different problems. Like, let's try this one. So example, say 6.1.9. Okay, so it's an example 6 point, so it's exercise 6.1.9. It goes like this. Let the table, which is x and frequency, so 0, 1, 2, 3, 4, 5, and here the numbers are 7, 14, 12, 13, 6, and 3, represent a summary of samples of a random sample of size 55 from a Poisson distribution okay. Find the maximum likelihood estimator of p of x equals to 2. Okay, let's do that. So we are trying to find a maximum likelihood estimator for p equals to for probability of x equals to 2. Right now, this problem has two parts, though it's not mentioned so. So follow it carefully. So the way we'll do it is, first of all, remember it's a Poisson distribution, and Poisson distribution is always characterized by its parameter lambda. How do we find lambda? We have done this before. So we have seen this before. So here's the solution. So let lambda be a parameter, denote the parameter of the Poisson distribution. Okay. We have seen this before, that the maximum likelihood estimator of theta, lambda, is x bar. We have seen it before when we studied the MLE for x bar. In fact, it's one of the problems from your exam. So there we have seen that the MLE for lambda is x bar. Okay. So therefore, what is x bar in this problem? So for this problem, so for the realization, we have x bar is what? So So it's x bar is 0 times 7 plus 1 times 14 plus 2 times 12 plus 3 times 13 plus 4 times 6 plus 5 times 3, isn't it? So note that 0 repeats 7 times, 1 repeats 14 times, 2 repeats 12 times, 3 repeats 13 times, 4 repeats 6 times, and 5 repeats 3 times. So if I want to compute how many times, like what is the sum of all these values, I'm just multiplying 0 times 7, 1 times 14, 2 times 12, 3 times 13, 4 times 6, 5 times 3, right? And I have to divide by the total number of whatever we have, and the total number is 55. So x bar, so what is 55? So if you add all this, it's 55. Okay. So there are 55 observations. So that is basically 116 over 55. Okay. So therefore, so that means x bar equals to 2.11. So that's the realization x bar. Okay. Now, what is the by invariance principle? So by the invariance of MLE. I'll write that later, but let's see what is probability of x equals to 2 in the regular case. It's really e to the minus lambda, lambda to the 2 over 2, right? So that's the regular case. So by the invariance of MLE, I can write that probability of x equals to 2, its estimator. So this is basically, I'll replace all these estimators by whatever we found. So it's e to the minus x bar squared over 2. And this is where we are using the invariance of Emily, meaning that if this is a function, I mean, if your lambda is estimated, then any function of lambda, like this one, this is a function of lambda, right? So note that what it says. So if we know this theta, so a function of this theta, its maximum likelihood estimator will be g of theta hat, right? So we know this lambda, so a function of lambda, it will be estimated by whenever I just replace this lambda values with its estimated value. Okay, so in our case, so and this is coming from the invariance of the MLE. So hence, for the given data, so the problem is find the MLE for probability of x equals to 2. The MLE for x equals to 2 will be equals to 2, its estimator is e to the minus x bar is estimated by 2.11. So it's 2.11 squared over 2, which is approximately 0.2699. So the maximum likelihood estimator for probability of x equals to 2 would be this quantity. Okay, this is one of the ways of computing the maximum likelihood estimators. Okay, and using the invariance principle. Now, since we have done one example just before this one, which is regarding the binomial, let me also solve another problem which is very much similar to what we have just done. Namely, let's see. This problem is problem number 6.1.7. So here is an example. 6.1.7 exercise. Okay, it goes like this. Let the table say x and frequency, and the table gives you 0, 1, 2, 3, 4, and 5, 6, 10, 14, 13, 6, and 1 represent a summary of sample of size 50 from a binomial distribution having n equals to 5. Find the maximum likelihood estimator of probability of x is bigger than 3. Okay. Again, this is an application of both the binomial thing that we discussed and the invariance principle. Here is a solution. Okay. All right, so let's consider, let P denote the parameter, the means the other parameter, n equals to 5 is known, the parameter of binomial distribution, meaning that probability of x equals to x is really 5, choose x, p to the x, 1 minus p to the 50 minus x for x equals 0, 1, 2, 3, 4, and 5, right? Okay. Now, we have already seen how to compute the maximum likelihood estimator for P. Okay. So let's see. So the probability of x bigger than 3 would really mean I from 3 to 5, 5 choose x, p to the x, 1 minus p to the 50 minus x, right? So that's what we are trying to estimate. We want to find MLE for this. So the maximum likelihood estimator for this object. Okay. Now we'll do it in a different way. Well, first, we already know what's the maximum likelihood estimator of P. Okay, so we know that MLE of P is P hat, where what is P hat? P hat is really, remember, it's X bar over N, or in this case, I think we wrote it X bar over N, right? So what is X bar in this case? For this case, for the given problem, given data, find that X bar would be what? So X bar is basically multiply all the frequencies and add. So I'll leave it up to you. But once you compute this, you'll get something like, let's see, 106 divided by 5. Divided by 50. Or 5. That's X bar. Okay, you can check. And so the way to do it is just by, so basically we are just multiplying and adding, and then so here sum is 50, so it's 50. So what is the likelihood estimator for p var? So in this case, p hat would be 106 over 50, and we have to divide by n. N is 5, right? So it's basically 106 over 250. So that number is approximately 0.424. So that's my p hat. As soon as you get this p hat, you are just using p hat right here for estimating this one. Okay? So using 1, hence using 1, we obtain the maximum by obtained by, and this is important, by the invariance of MLE. The probability of x bigger than equal to 3, its estimator, would be I from, so whatever we wrote here, I will replace everything. So here I'll write this, will replace p by p hat that we just obtained. This is my p hat. So this is I from 1 to 5. 5 choose x, p hat to the x, 1 minus p hat to the 50 minus x, where we found p hat to be 0.424. So if we just plug it here and compute this, you'll get p of x bigger than 3, its estimator is 0.3597. Okay, so that is the MLE for the binomial case when x bar bigger than 3. So it sort of shows you two different things. One is it uses the fact of the MLE for the binomial distribution, and then it uses the invariance of MLE to compute this. Okay? So that's why this invariance of MLE is a very, very powerful property, which is heavily used in practice. Okay. Now, couple of last remarks for today. So one thing is, let's write two theorems. Okay, so the first theorem, it goes like this. It's about the, existence of the MLE. Okay, so assume that x1, x2, xn satisfy the regularity conditions R0, R1, and R2 that we wrote at the beginning of today's class. So don't worry too much about this at this point. Where theta 0 is the true parameter assume further that this f of x theta is differentiable so we are assuming that this f of x theta is differentiable with respect to theta when theta is in omega. Okay. Then the likelihood equation d of L d theta equals to 0, or equivalently d of L theta d theta equals to 0, both, okay, has a solution theta n hat such that theta n hat in probability goes to theta 0. So it guarantees the existence of the solution provided it has a solution. So it says that it has a solution that goes to theta 0 in probability. Okay. Once again, what does it say? So it says that suppose this theta 0 is a true value, right? True value means we don't know what it is. So theta 0 is something we're trying to estimate. Now, what we are saying is, suppose this likelihood equation that we are solving so far, either this one, or actually we are solving this one. So suppose this, we are setting this equal to 0. And we assume that, I mean, we can solve it and we found a solution. I mean, it may have bunch of solutions, but suppose we find one solution, which is theta n hat. Okay. It guarantees that one of the solutions of this equation under, I mean, if the regularity conditions are satisfied, must go to the true value in probability. Okay. Now, let's write, I mean, this is actually too broad in the sense that it's not really, I mean, it's kind of vague, that it discusses the solution of the equation. I mean, it discusses, I mean, there is a one solution and this is going to the true value. So, I mean, it's not really telling us very clearly anything, though it's a very important theorem. But the next version that I'm going to write will make it more clear. And here is my next version. So here is a corollary. And this goes like the following. So assume that x1, just like before, x2, xn satisfy R0, R1, and R2. So the conditions you can check, that is the assumptions, where theta 0 is the true parameter. Further assume that f of x theta is differentiable with respect to theta in omega. Suppose the likelihood equation has a unique solution theta n hat. Okay, this is a very important statement. So that means what we are saying is, so that is dl theta d theta equals to 0, or equivalently d of l theta d theta equals to 0 has unique solution. Just one solution. Okay. Then the conclusion is theta n hat is, and the solution we call it theta n hat, is a consistent estimator of theta 0. And what is the meaning of consistent estimator? We have done it before. So that is theta n hat is going in probability to theta 0. Okay. So that means we can use this as a maximum likelihood estimator. Okay. So in other words, so we can basically use this quantity as the maximum likelihood estimator. Okay. This is a very wonderful theorem, which shows that if you can find a unique solution, then basically you're done. You don't have to, I mean, you already know that is a consistent estimator, meaning that this is true. Okay. So these are some of the aspects of this maximum likelihood estimator. So next class, what we'll do is we'll be solving some of the problems based on this result, especially the last result, because this last result shows that there is a very nice way of finding the maximum likelihood estimator based on a given set of data, and the estimator will be consistent. If you can find it's unique, we are done. Basically, it's consistent. So this will have a lot of implication in the practical application. So we'll see all those things in the next class. Okay. All right. So thank you. See you in the next class.